Welcome back to this explainer. Right, today we're tackling something that honestly feels like an absolute alphabet soup of confusing acronyms. I mean, if you've ever found yourself staring at terms like JVM, JRE, or JDK, and kind of just scratching your head wondering how on earth they actually fit together, well, you're in the right place. Our goal today? To totally demystify the hidden architecture of Java. We're not just skimming the surface here. We're going to use first principles to really understand how a Java program makes that incredible journey from the code you type on your screen all the way down to actual execution. But first, I've got a classic question for you. It's one that comes up in literally countless technical interviews. Is Java a compiled language or is it an interpreted language? Think about that for a second. It sounds like a super simple multiple choice question, right? But actually answering it requires us to fully understand exactly how a Java program runs under the hood. So keep that question tucked away in the back of your mind as we start breaking things down.
Okay, here's our roadmap for today. We'll be covering the journey to bytecode, compilers versus interpreters, the core engine, which is the JVM, zooming out to the JRE and JDK, decoding Java additions, and finally, running your first program. Let's get right into it. Section 1. The journey to bytecode. Let's trace a simple piece of code from the exact second you type it out.
Imagine you've just written some Java source code. You save the file with a .java extension. Let's just call it hello.java. Now your computer's hardware, it literally cannot read this file. It only speaks zeros and ones. So step 2 is passing your source code through a compiler. But here is where Java does something pretty unique. The compiler doesn't just instantly translate your code into machine code for your specific computer. Instead, it generates an intermediate format. That's step 3, generating bytecode. And this bytecode, it is completely platform independent. Which brings up a massive fundamental question. How does a single piece of bytecode run on literally any platform? Think about it. A Windows PC with an Intel processor is structurally totally different from a Mac running an Apple Silicon chip, right? Their native machine languages just aren't the same at all. So how does this universal bytecode actually execute on such entirely different machines?
Section 2. Compilers versus interpreters. To solve that cross-platform mystery, we first need to quickly look at the two main ways computers translate code.
So there's a really stark contrast between these two translation methods. On one side, you have a compiler. A language like C++ uses a compiler to read your entire source code file all at once, instantly converting the whole thing into machine code. It's incredibly fast to run once it's actually compiled. On the flip side, we have an interpreter, which is used by languages like Python. An interpreter takes your source code and translates it and then executes it just line by line by line.
And this brilliantly answers our hook question from earlier. Is Java compiled or interpreted? Well, it's actually both. Java takes this really clever hybrid approach to pull off its famous write once, run anywhere portability. First, it acts like a compiled language, converting your .java file into that intermediate bytecode all at once. Then it shifts gears. It acts like an interpreted language, reading that bytecode and translating it into machine code on the fly for whatever specific device it happens to be running on.
Section 3. The core engine, the JVM. So what exactly is doing all this on-the-fly translation? Let's zoom in on the central piece of the architecture.
JVM stands for Java Virtual Machine. You can basically think of it as a simulated virtual computer living inside your actual physical computer. And here's the kicker. Every platform, Windows, Mac, Linux, has its own specific tailor-made JVM. When you bring your universal bytecode over to a Windows machine, the Windows JVM takes that bytecode and translates it into the precise zeros and ones that the Windows CPU needs. That right there is the absolute magic of platform independence. But how the JVM handles this translation has actually evolved over the years. Back in the 1990s, when Java was really blowing up, hardware was slow, RAM was super limited, and disk drives moved at a total snail's pace. Because of that, early Java relied entirely on an interpreter inside the JVM to read bytecode line by line. They just wanted the program to start running immediately, without waiting for some massive compilation process. But as hardware got remarkably faster, modern Java evolved a way faster hybrid approach right inside the JVM itself.
Modern Java introduced the JIT, or just-in-time compiler, right alongside the interpreter inside the JVM. And the JVM is incredibly smart. It actually watches your bytecode as it runs. When it spots a chunk of code being executed over and over again, really heavy, frequent operations, it hands it straight over to the JIT compiler. The JIT then instantly compiles that entire chunk directly into machine code for a massive lightning-fast speed boost.
Meanwhile, the interpreter just keeps quietly, methodically translating the less frequent everyday code line by line in the background. It's really the perfect balancing act.
So the absolute key takeaway here is that the JVM is a total workhorse with three main jobs. First, like we just covered, it converts bytecode to machine code using that interpreter and JIT compiler combo. Second, it provides absolutely vital security through a sandbox model. Because Java is portable, you might be downloading bytecode from the internet, right? Well, the JVM runs this code in a restricted, virtual sandbox to prevent any malicious code from messing with your files or dropping viruses on your real machine. And third, this is a lifesaver. It handles garbage collection, automatically managing your computer's memory, so you literally don't have to worry about it.
Section 4. Zooming out to the JRE and JDK. So the JVM is just the inner engine. Let's look at the concentric circles of tools that wrap around it, the actual software you install in your computer. Wrapping directly around the JVM is the JRE, the Java Runtime Environment. Now, if you only have a JVM installed, your code actually won't run properly. Why? Because it needs basic building blocks. If your code tells the computer to print text to a screen, the JVM doesn't inherently know how to do that. It needs internal, pre-written code to execute that command. We call these class libraries. The JRE packages the JVM together with these essential class libraries. Long story short, if you want to run a Java program, you absolutely must have the JRE.
But let's step back even further to the largest circle, the JDK, or Java Development Kit. The JDK contains the JRE, which of course has the JVM inside it. But the JDK adds the ultimate tools for a programmer. It includes the compiler. That's the tool that actually converts your raw.java source code into bytecode in the first place. It also includes development tools like debuggers to help you step through your code and squash errors. The JDK is the complete master toolkit. You need it not just to run Java, but to actually write, build, and develop Java apps from scratch.
Section 5. Decoding Java Additions. Now, before we run our code, let's quickly clear up the rest of this alphabet soup that notoriously trips up beginners. You're going to hear these terms thrown around a lot. First is JSE, Java Standard Edition. This is core Java. It's what you use to learn the basics and write your standard everyday programs. Then there's JEE, Java Enterprise Edition, which is for heavy-duty web applications and things like Spring Boot. Though, side note, it's actually known as Jakarta EE now. Finally, there's JME, Java Micro Edition. This was originally designed to run on early, lightweight mobile phones. Honestly, you can pretty much ignore this one today. It's completely obsolete because modern mobile apps are all built using Android and Kotlin.
Section 6. Running your first program. All right, we've mastered the theory. Let's see how all of this comes together in a real-world scenario. Imagine we open up an editor, like VS Code. Step 1, we write a basic script and save it as demo.java. Step 2, we jump into our terminal and type the command java c demo.java. That C at the end of Java, it stands for compiler. Because we have the JDK installed, it grabs our source code and compiles it. Step 3, it spits out a brand new file called demo.class. And there it is. That .class file is our platform-independent bytecode.
Now we actually want to see it work. Step 1, we go back to the terminal and run the command java demo. This triggers the execution phase. Step 2, the JRE steps in, bringing all those essential class libraries and hands the bytecode over to the JVM. The JVM's interpreter and JIT compiler take over, translating that bytecode into machine-specific zeros and ones. Step 3. Your CPU takes those zeros and ones, executes them, and finally, Hello World pops up on your screen. You know, seeing that output is always rewarding, but truly knowing the journey it took to get there is what makes you a real engineer. True mastery comes from understanding the architecture, not just blindly memorizing the syntax. Knowing exactly how the JDK builds the code, how the JRE provides the libraries, and how the JVM translates and secures the execution. That gives you a massive advantage over developers who just don't know what's happening under the hood.
So I'm going to leave you with a bit of a challenge. Are you ready to stop passively watching? It is time to apply these first principles. Go download the latest version of the JDK, figure out how to set your system's path variables, and run your very first line of code straight from the terminal. Go get your hands dirty. Because the next time you hit run, you won't just be hoping it works, you'll know exactly the hidden engine making it happen. Thanks for joining me on this explainer, and I will catch you in the next one.